Swayam Prabha. Digital India. Educated India.
Hello all, welcome to Astrochemistry. This is going to be lecture number 71. Now in the previous lecture, I think I had introduced you to the basic aspects of thermodynamics and kinetics relevant to astrochemistry. I think the exact stop, the point where we stopped in the last lecture was with the introduction of, in lecture 70, we had discussed about the various thermodynamic parameters, your free energy, enthalpy, internal energy, and entropy, correct? So we had discussed about all of these things. So today, we should be slightly looking at the significance of this quantity called as G, that is the free energy available. Now, having introduced G, one very important thermodynamic criterion for chemical reactions in the interstellar medium to occur is that your delta G net, that is, say for example, consider an interstellar reaction of the form this is very generic, very generic, but I've just given it in this way. Now, for this reaction, assuming that it can happen in the gas phase, it can also happen via a surface on an ice grain, that is, but it doesn't really matter for our purpose. Regardless of what this reaction is, for a reaction in an interstellar medium, to even be plausible, right? The delta G should be negative always. Now delta G negative means that free energy is liberated, so delta G negative implies that liberated, all right? In other words, to form some products in the interstellar medium, you need the liberation of energy. Especially, it should be free energy, all right? Because the free energy also takes into account the contribution of entropy, as we very briefly discussed in the previous class. So delta G should be negative. This condition is what is called as delta G is negative. That is, this condition, delta G is negative, is what is commonly called as a reaction being exergonic, all right? So a reaction for an interstellar reaction to be possible, the delta G should be negative. I make this point very clear. I'm not saying that the reaction will happen, for the reaction to even be possible, So for this reaction to be possible, so why is it? Well, the reason is that there are not many sources of energy, right, in the interstellar medium. When I say many sources of energy to carry out chemical reactions, let's say that because the interstellar medium is actually, the number density is very low, right? It is very sparse, very less dense, as they call it, right? So therefore, when the source of energy, there is not a significant source of energy for the reactions to be carried out. The reactions, only those reactions are feasible wherein the net free energy is going to be liberated, right? And that's why your delta G should be negative, The reason is that is overall the sparsity of the ISM, not many sources to supply energy to mediate the reactions. See, I'm not saying that the interstellar medium is not a source of any energy at all. That would be a wrong statement. I'm only saying that to lead to a specific reaction, a specific chemical reaction, or to facilitate a chemical reaction, you don't have the energy. All right. Of course, the interstellar medium is a source of tremendous energy. You have all kinds of interstellar radiations. You have magnetic fields. You have cosmic rays, etc., etc. Okay. But please understand that having some energy is different from having energy to facilitate a particular reaction. All right. So that is why the reaction itself should result in the liberation of energy for the reaction to happen. Please do this distinction. Okay. Right. To supply energy, to facilitate, to supply energy for the facilitation of any particular reaction. Okay, please note this point. Now you may be wondering, well, isn't this criterion the same on Earth as well, right? Of course, it is very similar on Earth too, but there is one key distinction. Especially if you're familiar with a lot of biochemical reactions, you see that sometimes some of those reactions could have a delta G as being positive. In other words, you can have what is called as endergonic reactions also, but they are coupled with other set of chemical reactions which are hugely exergonic. In other words, some reaction for which the net delta G is positive shall be coupled with another reaction for which the delta G is exceptionally negative, so that overall what happens is that you have a negative delta G. Okay, but that situation is not possible in the ISM owing to the sparsity of the ISM. So therefore, for any reaction to happen, the reaction itself should be liberating free energy. Are we clear? So this is the criterion for the thermodynamic criterion for a reaction to occur. But hey, this is not all, right? It's not all. On top of the delta G being negative, if you go back to the first few lectures, perhaps around lectures 9 or 10, I told you that the energy should be liberated. But more precisely speaking, it should be the free energy which should be liberated. Okay, please note the distinction. It is not delta E, but delta G. I'm talking in comparison with probably lecture 9 or 10, when I was introducing you to the differences and similarity between the interstellar medium and Earth. Okay, so please note this point. So delta G should be the criterion for deciding the possibility of chemical reactions happening in the ISM. Okay, now the next point is, always remember that on top of the delta G being negative, that is a reaction being exergonic, the next important criterion is that there should be some way to transfer the excess energy. Okay, so delta G negative, delta G is negative, right, along with a source to transfer the excess energy liberated in the formation of the products. Okay, to transfer the excess energy liberated is also important. I would say more than important, is also essential for interstellar reactions to be occurring. So what did I just say? There are two thermodynamic criteria for interstellar reactions to be possible. One of them is that, the first step is that free energy should be liberated. Okay, it is not just energy, but it should actually be the free energy which should be liberated. Okay, point number one. And the next point is that on top of free energy being liberated, the excess energy of free energy that is liberated, that should be transferred to some other particle, so that the backward reaction again doesn't happen. That is also why, remember that we've always been worrying about reactions of the form A plus B giving C plus D, and also why the H plus H does not give you H2 directly in the gas phase, right? So this excess energy transfer is mediated by processes such as radiative association or the participation of surface as an effective third body. Remember, We saw it a few lectures earlier. Okay, so please note this point. So these are the thermodynamic criteria for reactions in interstellar medium to be plausible. So these are the thermodynamic criteria. I mean, it may not be clear what I've written. Thermodynamic criteria. Okay, right? For a reaction to occur in ISM. In fact, more than occur, this is just a plausibility condition. It is not that if it is satisfied, the reactions will definitely happen. Because what is the more important thing? Well, along with thermodynamics, kinetics is equally important, right? Please note this. All right. So now, before I go to the next point, notice one very interesting feature, about the thermodynamics of the reactions happening in space. It is that, now consider this for example. So I'm moving on to the next related topic in thermodynamics, beyond plausibility, which distinguishes between how chemical reactions happen on Earth vis-a-vis how chemical reactions happen in the ISM. Now consider, for example, some reaction of the form, okay, say something like half H2 plus CO. Let's say that this is happening in the gas phase. Is giving me HCO plus electron in the interstellar medium. So let's say that all of this is happening in the gas phase. All right. It could also be happening via the participation of an interstellar grain. Now, this is a very important reaction en route to the formation of formaldehyde and HCO also. So this is one of the steps which is well studied in the literature of interstellar reactions. Now, if you consider this reaction, notice that this is one complete balanced equation. So chemical reactions, be it on Earth or in the ISM, do not always happen exactly the way the final equation is written. Okay, please note this point. Chemical reactions do not always occur in the final balanced way it is expressed. Or does not occur via, I'll phrase it better, via the final balanced equation. This is equation. It is expressed. So this is just one balanced equation, but chemical reactions don't always happen like this. That is in one step. It is like, you form like you generate H2 and CO, and then you make them collide, and naturally they will be forming. Okay, right? That is not how things work. Instead, what happens is that this is both on Earth and in the ISM. Please note this. Okay, both on Earth and in the ISM. This is common. Okay. Instead, so how this actually happens is, let's say you take some H2, you take some hydrogen in the interstellar medium, right? When I say you take, it's a colloquial phrase. Of course, you can't go to the ISM and take the H2 itself. So you take H2, and due to either bombardment by some cosmic rays or by photodissociation, you can form this species, H2 plus electron. Let's say everything is happening in the gas phase. Okay, so I've already stated this here, so I don't need to repeat the phase here. Let's say this is one step that is happening. Now, followed by this, H2 plus, right, can react with H2 to form H3 plus H. You think about this reaction. This was in fact one of the very first reactions that we discussed in this course itself, right? As how reactions that would normally not happen on Earth could also happen in the ISM readily. Okay, so it has been found that this particular reaction happens via a sequence of steps, right? This is based on various thermodynamic and kinetic calculations. Okay, I will come back to the details very soon. For now, just note that this reaction occurs via a series of steps. So this is step 1, and this is step 2, and in the next step, your CO comes in, H3 plus. If you want, the balancing of, the balancing is already done. So next what happens is your H3 plus reacts with carbon monoxide to form HCO plus, right? And liberates H2 again. So if you add all these three equations, 1, 2, and 3, you will be getting this. Okay. In other words, what do I mean by say add? What we're talking about is all of these reactions are happening in sequence, all right, to overall get this particular chemical reaction. So each of these individual species, that is your H2 plus, your H3 plus, not the electrons, of course, your H, etc., etc. Your let's call this equation 1, 2, 3. We've already named it. The products formed, okay, that is my H2 plus, H3 plus, and HCO plus. They are all what are called as intermediates. Sorry, not HCO plus. That is the final product. My apologies. Okay. H2 plus and H3 plus are what are called as intermediates in this multi-step chemical reaction. Okay. In this multi-step please note this carefully. So these are the intermediates. Like I told you earlier, that the fact that this chemical reaction overall, it is happening in the ISM suggests that it should, how do we know it happens? Well, there are some experiments through which we strongly believe that this is one plausible way via which HCO plus is formed. Okay. So of course, always note, whenever I say that some chemical reaction is happening in the ISM, I or nobody else has actually gone there and performed the experiment in the interstellar medium itself. It is that through a series of highly calibrated and careful calculations and experiments, we believe, and we have very good reasons to believe, that this is one very important reaction for the formation of HCO plus in the interstellar medium. All right. So now in this reaction, these are the intermediates. Now, the fact that, this is a reaction that's happening in the interstellar medium tells us that the delta G for this overall reaction is negative. So the delta G is overall negative for this process. Please note that. Now, likewise, for each of the individual steps also, the delta G is negative. Okay. Let's call the magnitude of the delta G as like delta G1. That's of course a negative number once you consider the sign also, but we are considering, the magnitudes only. Now this is delta G2. And this is delta G3. So these are the magnitudes of the delta G's. Now, there is one beautiful concept in the ISM which is not noted on Earth. It is that on Earth, many multi-step chemical reactions, okay, right? I'll just call this MCR, just for ease of writing. All MCRs. What are MCRs? Multi-step chemical reactions. They go towards this, which has the maximum magnitude for G given enough time. This is a very important point. All right, this is what is called as thermodynamic control. In the ISM, please note that it is not necessary that the product, okay, right? The product or the step resulting in the max value of delta G, the magnitude, okay, right? The max value of delta G needs to be formed. The product, it is not necessary that the product which results in the maximum delta G need not I'll put it this way, the product resulting in the maximum of G need not be formed. Okay, please note this point. In other words, thermodynamic control is absolutely important in on Earth, but it is not all that important in the ISM for the reasons we're going to talk about while we discuss the module on chemical kinetics for astrochemistry. I'm coming to that in a bit. Okay, so please note this point carefully. In other words, let's say that, let's say some specific product such as HCO plus is formed via a sequence of reactions. Okay, say something like A plus B giving C, that gives D, and then that gives E plus F. Some reaction, okay, right? We can take a generic example. Now, let's call this like C is intermediate 1, this is intermediate 2, and these are the final products. Now, if you were to, map the free energies, okay, let's call this reactants. If you were to map the free energies of all these species on Earth, so let's say that these are the reactants. Arranging my reactants, the intermediates and the final products in terms of, let's say that the delta G for the reactants is somewhere here. Let's say that the intermediates, okay, their delta G is somewhere here. And I2, let's say, is somewhere here. And the final product is somewhere here. So this is, in terms of mod delta G, let's say here is the, I would say mod G, sorry. So, see, as far as reactions are concerned, we talk about delta Gs. As far as the individual entities are concerned, we're talking about the G values themselves. Okay, please note this point. So, this is the sequence in which the magnitude of G is there. Okay, now this reaction can still lead to the final product because with respect to the reactants, the final products are lower in free energy. So this can occur in the ISM, but the point is, but will not occur on Earth given enough time. Okay, given enough time. Now this is all I'm trying to say all along. All right, so the point is, you can start with the infinitely separated reactants, right? And even if some intermediate were to be lower in free energy than the final products, right, in the ISM such reactions are also feasible. What is the reason? The reason is that on Earth, given enough time, there's a possibility of enough number of collisions to happen. Okay, so while these collisions happen, eventually, given enough time, that depends on the rate of the reaction, right, which we'll come to very soon. So given enough time, what can happen is that the most stable product can happen. But in the ISM, due to the much lower number density, okay, much lower number density, not all collisions are going to be feasible. So you can always, form, as long as, it is lower than the reactants, and assuming that, there is some source of energy dissipation, that's always important, okay, then some higher energy species on a relative scale, even that can form higher energy with respect to the intermediate form. Okay, so this is a very key important aspect, thermodynamic aspect of the interstellar medium. All right, so I will now sum up, like what we saw in today's lecture. So the thermodynamic summary, right, as far as the interstellar reactions are concerned, are thermodynamic summary for reactions in ISM. 1, A, delta G should be negative. B, this allows for possibility. All right, delta G should be negative. The next step, the next point is that excess free energy should be transferred, successfully, right? Otherwise, the product will go back to the reactants. And C, note that thermodynamic control. Which is this phenomenon, that is that it is not necessary that the most stable product has to be formed. Okay, in the ISM is not as important as it is on Earth. Because on Earth, if you give some reaction enough time, right, the most stable species will form. However, in the ISM, that need not be the case. What is it due to? Point C is due to, again, the sparsity of the ISM not resulting in enough collisions. The sparsity implies, therefore, that collisions will be far fewer. Okay. But the possibility of collisions being very less likely in the ISM, thermodynamic control is not as important. So with this, we end this lecture. And in the next module, we shall be discussing about the chemical kinetics, which is relevant in the interstellar medium. Thank you.